Welcome back to The Explainer. Today, we're stepping right into the shoes of chemical detectives to track down and identify the invisible elements literally floating all around us. So let's dive right into this fascinating problem. How exactly do you catch and profile a suspect you can't even see? I mean, we're completely surrounded by colorless, odorless gases. But in the lab or out in the field doing environmental testing, knowing exactly what gas you're dealing with is absolutely critical. You obviously can't just rely on your eyes, right? You need a rock-solid, strategic approach to decode the chemistry happening right under your nose. To solve this, we're building an investigative toolkit moving through 5 crucial steps. Meet the invisible suspects, the fire tests, the bubble test, the litmus interrogations, and we'll wrap it all up with the detective's summary. All right, Section 1, meet the invisible suspects. Let's lay out the lineup of the 5 tricky gases we're going to profile today. Our suspect list includes hydrogen, oxygen, carbon dioxide, ammonia, and chlorine. Now, each of these gases has totally unique chemical properties, but because they often look exactly the same when they're just sitting there trapped in a test tube, we need a very specific tool from our kit to force them out of hiding and reveal their true identity. Moving on to Section 2, the fire tests. This is where we bring out our first and probably most dramatic tool to test our first 2 elemental suspects: combustion. Let's start with hydrogen. For this one, you just hold a burning splint right at the open mouth of a test tube. You actually have to be careful not to shove the splint all the way down into the tube. Just hold it at the top, because the gas actually needs the surrounding air to burn. If your suspect is indeed hydrogen, it rapidly combusts with the oxygen in the air to produce water, and this rapid reaction creates a highly distinctive, really loud, squeaky pop sound. It's this incredibly satisfying, unmistakable, auditory positive result in the lab. Now, conversely, to test for oxygen, we use a slightly different fiery approach. You take a splint, light it, and then blow it out so it's just glowing. Make sure it's not completely dead. Then place that glowing splint inside the test tube of gas. Because oxygen actively supports and literally enhances all combustion reactions, that little splint will miraculously reignite and burst right back into flames. Sometimes it might just glow exceptionally brightly, which technically counts as a positive result, but that full reignition, that is the definitive proof you're looking for. So, here's a brilliant examiner tip, because it is super easy to mix up the tests for hydrogen and oxygen. Just remember that a lighted splint has an H for hydrogen, while a glowing splint has an O for oxygen. It's such a simple, elegant mnemonic, but it perfectly separates our first 2 invisible suspects every single time. Okay, Section 3, the bubble test. Let's transition away from fire and get into precipitation to examine our next suspect. This tool is tailor-made for carbon dioxide. If you bubble CO₂ gas through an aqueous solution of calcium hydroxide, which, as you probably know, is commonly called limewater in the lab, you get this highly visible reaction. The limewater starts off completely clear and colorless, but introduce some CO₂ and that liquid will quickly turn milky or cloudy white. Now, we've got to address a really common misconception here. A lot of students fall into the trap of thinking that just snuffing out a flame proves they have carbon dioxide. And, well, sure, CO₂ extinguishes a flame, but guess what? Other gases, like nitrogen, do the exact same thing. So an extinguished splint is absolutely not definitive. The limewater bubble test, that is your only true, irrefutable proof. And this brilliantly illustrates the underlying chemistry happening during the bubble test. The carbon dioxide gas combines with the water to form carbonic acid. Then, that acid reacts with the calcium hydroxide in the lime water. This reaction literally creates calcium carbonate, which is essentially just chalk. That chalk precipitates right out of the solution, creating these tiny, insoluble white particles that make the water look all milky. And what's fascinating is, if you keep bubbling CO₂ through it for a long enough time, it forms carbonic acid again, which reacts with the chalk to create calcium hydrogen carbonate, dissolving that chalk right back into a totally clear, colorless solution. Talk about a neat party trick. Moving right along to Section 4, the litmus interrogations. Now we're graduating to the trickier and honestly much smellier interrogations using chemical indicator paper. Our 4th suspect is ammonia. This gas has a very characteristic, sharp, choking smell. To definitively test for it, you just hold damp, red litmus paper near the mouth of the test tube. Since ammonia is basic, it's going to turn that damp red litmus paper a distinct blue. You just have to be super careful not to touch the sides of the test tube, especially if you made the ammonia using sodium hydroxide, because that sodium hydroxide itself could touch the paper, turn it blue, and totally ruin your results. Alternatively, there's another awesome test. If you react ammonia gas with hydrogen chloride gas, it creates this highly visible, dense white smoke of ammonium chloride. It looks like a magic trick. Oh, and please don't mix up your suspects here. It's such a common pitfall. Remember that ammonium, ending with an is the aqueous cation, NH₃+. Ammonia, ending with an A, is the actual sharp-smelling gas, NH₃, that we're hunting for today. Precision in our detective terminology matters just as much as our lab work, right? Now, for our final suspect, chlorine, we absolutely must exercise extreme caution. Because it is highly toxic, these tests should strictly be handled in a fume cupboard. We have to ensure the atmospheric concentration doesn't exceed safe limits, like that strict 1.5 milligrams per cubic meter threshold for a 15-minute exposure. You know, it's commonly used to kill microbes in public water supplies and pools, but in an enclosed laboratory space, it is incredibly dangerous. But when properly handled, the test for chlorine is visually stunning. When damp blue litmus paper is introduced to a container holding chlorine gas, it goes through this fascinating two-step color change. First, the blue paper briefly turns red, and then, boom, almost like magic, it ends up completely bleached white. Let's zoom in to the microscopic level to see exactly how this goes down. First, you have to dampen the blue litmus paper with deionized water. The chlorine gas reacts with that water to form two different acids, hydrochloric acid, or HCl, and hypochlorous acid, HClO. The strong hydrochloric acid drops the pH immediately, turning the blue indicator dye red. But then, the unstable hypochlorous acid decomposes, releasing a highly reactive nascent oxygen atom. This nascent oxygen is an incredibly powerful oxidizer. It literally acts like a molecular sledgehammer, breaking the chemical bonds within the dye's chromophore, which, if you remember, is the part of the molecule responsible for its color. By smashing up this structure, the dye loses its ability to absorb visible light, permanently altering the chemical structure and bleaching the paper completely white. And that brings us to Section 5, the detective's summary. We've built our toolkit, we've successfully caught all our invisible suspects, so let's pull all our findings together into one clear lineup. Here is your ultimate detective's cheat sheet. It summarizes exactly which chemical tool matches which invisible gas, alongside the undeniable audio or visual proof of their identity. We have hydrogen responding to a burning splint with a squeaky pop, oxygen dramatically relighting a glowing splint, carbon dioxide reacting to precipitate chalk, turning limewater milky white, ammonia turning damp red litmus paper blue, and finally, toxic chlorine reacting with water to turn damp blue litmus red before completely oxidizing it and bleaching it white. This table right here, it's your absolute gold standard for identifying these foundational elements. So what should you really take away from this explainer? It's the sheer power of scientific observation. I mean, if these basic chemical reactions, a simple wooden splint, a little bit of lime water, some damp colored paper, if they can definitively decode the very air we breathe and reveal the invisible world right in front of our faces, just imagine what else we have yet to uncover. Keep asking questions, keep observing, and never, ever underestimate the invisible forces shaping